Oke ya. Nah, oke. Ya, boleh ya. Kalau ada apa-apa soalan, boleh sila terus sampaikan ya. Sampai tunggu slide selesai, lecture selesai. Oke, assalamualaikum. Boleh nampak ya? Oke ya. Assalamualaikum. So we welcome again. So this is the second section of our lecture class, week 3. This is about MEMS fabrication. This section will include the pattern transfer, structure deposition, and removal. This is the basic process to fabricate MEMS structure or MEMS device. My name is Associate Professor Dr. Jumbril Yunus. This subject consists of first the pattern transfer, we call as lithography, the material deposition, and then we come to the material removal, and finally we will close our section with the case study, namely MEMS actuator. Yeah. So first we introduce about the MEMS fabrication. Actually, the technology of current MEMS fabrication process are adopted from IC process, batch process, called as batch process. So batch process means that the device structure is created a layer by layer, like this, yeah, layer by layer. The common techniques to fabricate MEMS structure are surface and bulk micromachining. Here we can see surface micromachining. That is the process to create the structure over the substrate. Yeah, this is the substrate. So we create the structure over the silicon substrate, such as the cantilever or its sacrificial layer, or like this. This example of bulk micromachining, in which the structure is created from the substrate, inside the substrate. So we add or we remove some material in the substrate to create the structure. This is example of MEMS membrane, silicon membrane. Okay, actually this structure can be fabricated by three basic process, namely transfer of mass transfer. This is especially for a top-down process. That means we create the layout using CAD, and then we transfer the layout onto the substrate, and then the deposition. This is the second basic process. The deposition means creating new layer, and then the removal, the removement of the unwanted material. Some other process in MEMS combine the standard IC and some electronic process, such as thick or thin film technology, molding, or electroplating, etc. Liga, micro molding, thick film printing, wafer bonding, electroplating, etc. While the material used for the MEMS fabrication is commonly coming from silicon, compound semiconductor such as 3,5 compound, 2,6 compound, gallium nitride, gallium arsenide, etc., glass, polymers, ceramic, graphene, etc. This is due to the material specific for specific application. So such as silicon carbide. This material is very specific. Is specific for very good for heat atmosphere, for in very hot condition. While compound semiconductor is suitable for optoelectronics application. Okay. Okay, this is the basic process to fabricate MEMS structure, such as layout transfer, material deposition, and material removal, as I mentioned before. This process actually can be repeated. We can repeat the process, such as after we create the pattern, we etch, we can redeposit. We redeposit the layer, and then we create another pattern, because this is the batch process. So the structure is created by layer by layer. There are two types of lithography for layout transfer. We can use mass lithography. That means lithography with the pattern is created by implementation of mass. Mass. This is for photolithography, soft lithography, or nano imprint layout transfer process. Another lithography is massless lithography, such as E-beam lithography, IB lithography, or laser direct write system. For material deposition, we know the process to create the layer can be done using a sputtering process or thermal evaporation of metal layer, CVD, spin coating, etc. So material deposition also can be used to create the sacrificial layer. Sacrificial layer means that the layer is deposited to support for creating another layer. After the creation of the layer, so we remove this layer. Therefore, we call as a sacrificial layer. And material deposition can be used for creating 3D active structure on the substrate, such as in surface micromachining process. Material removal, material removal can be used to create 3D active structure in the substrate, such as for bulk micromachining process. Yeah, the process can be the structure can be created by process etching or process lift off. We will talk about this process in detail in the next slide. So this is the schematic of process design. We take from the previous case study, namely fabrication of planar coil. So this is the step process. Initial process is cleaning process of the substrate, which already coated with a certain layer, namely isolation layer made of silicon oxide. Yeah? And then we do the first lithography. Yeah? So we create the pattern, and then we deposit metal here. The yellow is the metal, so we deposit metal by using sputtering or evaporation, and then we remove the lithography layer, photoresist. So we have this structure, the first metal layer, and then we coat with oxide, and then apply another photoresist, and we do the second photolithography to create the pattern, and then we etch here. So we have the channel to connect the first layer with the second metal layer here, and then deposit another. We do the third photography and deposit metal, and then we have two metal layer. That means two copper inductor layer. And we have the connection here. That means the bottom metal is connected with the top metal. This is the schematic of the process design. Okay, we come to the first basic MEMS process, namely lithography. Lithography is a process to transfer the layout design by CAD, the layout that is designed by our CAD tools, or to create a micro-sized pattern on a substrate. Yeah. This is an important step in MEMS fabrication, which is actually adopted from IC technology. The pattern transfer, if we use light exposure, is called as photolithography. This is to transfer the pattern from the design layout to the real device. This is we can see our layout can be print out on a transparency mask. So we have here the mesh in cross section view. So there is area, dark area, and transparent area. Transparent area, white area will allow the light go through to the photoresist. And then we develop the photoresist. We have the structure. Okay. So this pattern of the transfer is used to enable process etching and deposition, a selective etching, like here. So we can use this pattern to etch this area. So this called as a selective etching process, or to deposit metal here. Here, metal here, and then we remove here. So we have the metal over the silicon. The photoresist will prevent ion bombardment or etching from reaching region of the chip. Yeah, so using this pattern also we can remove photoresist and start with the new layer. The photoresist, yeah, is made of photosensitive polymer, yeah, and transparent sheet is used as the mask, yeah, to define the region that get exposed to light at its stage. For this process, for the photolithography process, we use optical wavelength between 250 up to 350 nanometer, and that means this should be the wavelength in UV light. So the photolithography process consists. So the photolithography system is consists of actually of UV exposure, the transparent mask, the photoresist, yeah, and also the substrate lah. Okay, we can see here if the light go through the mask, so it can attack the photoresist and later create the pattern here. Yeah, so this is some type of photoresist we call as positive photoresist and negative resist. Positive resist means the area which is sorry, the area which is contacted with the light, so yeah, will create the pattern. Yeah. Okay. Another type, the area with, for the negative resist, the area contacted with the light will remove the photoresist. To create the micro-size pattern or to transfer the pattern, we use a photolithography equipment. Yeah. So this is the schematic of our photolithography instrumentation or equipment. It consists of mask aligner. Mask aligner is used to adjust the position. Yeah, because we are creating the pattern layer by layer. That means the first, second, and the next layer should be in match position. This is very important, especially for multi-layer structure. The light exposure system. This is the light exposure system. This is the light exposure system using UV light in range 200 to 45 nanometer, and we have also here the mask photo mask system, yeah, which is located above our substrate. So we have here also the wafer loading system. This is the wafer loading system. Yeah? So this is the photograph. This is the schematic. This is the wafer loading system. So we can put our sample and put inside to the adjustment system, and will be contacted with the mask. So we have here also some button button to adjust the to adjust the vacuum system. This equipment is located in our clean room. Yeah, this is the photo mask. The mask consists of a transparent area that pass UV light through the glass plate. We put here our mask. We can print out this layout after we design using our CAD using CorelDRAW or AutoCAD, and then we print out on a transparency mask, and then we attach on a glass substrate. It consists of the white and dark area. This white and this dark. This dark area that prevent the light go through, passing through the glass. The photo mask is made for repeatedly transferring and desired pattern on resist coated wafer. The mask is put on chrome or glass plate, or we can also print with a high resolution printer on a transparency, which is then attached onto a glass plate. The masks are designed using computer aided design software. This is the layout of our inductor, coil inductor device. We have 3 masks. First mask is used for bottom metal layer, for bottom metal. The second mask is used to create the via hole, supaya this can be connected to the top metal. So the third mask is top metal pattern format for top metal. Okay. Before we start with pattern transfer, a photosensitive material coating process needs to be done. So we need to coat the substrate with a photosensitive material we call as photoresist. This photoresist is coated using spin coating process. Okay. Photoresist act as mask on substrate to prevent for process ion bombardment or for process etching for etching region of the chip. And then we need also developer to remove excess photoresist, and we can also start with the next layer. Spin coater is used for photoresist distribution, and we need also hot plate or oven to remove the water content of the resist. To remove the photoresist, so we can use acetone, propanol, or other removal solution. It depends on the type of the photoresist. So this is the how to coat the photoresist. We call as the spin coating process. This is done to distribute the polymer over a planar surface such as silicon or gallium arsenide, gallium nitride, etc. The thickness of the photoresist will determine the functionality of the photoresist. Thin photoresist normally used for the process metal deposition, or for sacrificial layer, or mask for soft etching, not hard etching, but soft etching process, because we just need the pattern. We are not we don't need the the amount of the photoresist. Just we need the pattern. While the thick photoresist is used for deep area etching or to create 3D structure. This thickness depend on the concentration of the material, the viscosity, the spin speed, or RPM. High RPM will reduce the thickness because the photoresist will spread out more. Yeah? And also it depends on the spin time. This is a picture of how to coat the photoresist. Yeah? We drop the photoresist and we let the stage spin. Spin. Okay, various photoresist type can be used depending on the quality and required thickness. AZ 100,500 is called as standard photoresist, commonly used in IC fabrication. This is actually thin for thin photoresist. Yeah, it can be coated up to 1.5 micrometer. There is another type of standard photoresist that commonly used in IC fabrication and also used in our lab, namely AZ5214E. We call this as negative photoresist. Another photoresist AZ4620. This is thick photoresist. Yeah. Has been implemented for certain 3D structure application. Some other photoresist, namely PMME, SUH, which are used for a specific application requiring a thick resist. Okay, this is a schematic of the process with a positive resist or with negative photoresist. So we have here mask light exposed with photoresist here. If the light go through, and then we develop, then we have the structure of a photoresist like this. Yeah. For negative photoresist, if the light go through the mask, so when we develop, this will create the structure. Yeah. Okay. Another lithography process is called as macromolding. This is also one of the common process in MEMS, which is used to transfer the micro pattern by pressing or by pouring the polymer material into prefabricated pattern. So this is a process step. So we have here prefabricated pattern. Yeah, we add or we let the photoresist, yeah, as the mold master, and then we pour our polymer material, yeah, after hard baking, so we can fill up this layer. Then we have this structure. This process normally we use to create a micro channel, like here we create the photomask pattern. We create the master mold master, yeah, and then we pour the PDMS layer, polymer material PDMS, and then we fill up. Then we transfer to another substrate. Then we have here the channel. Another type of common lithography process for the transfer of the micro pattern is macromolding, injection molding. So this injection molding similar to the soft lithography, micromolding. However, we apply injection press. So here we have two basic material, ceramic, powder with binder, and then we mix, and then we inject inside a pre-created structure. So we have here the mold structure, and then we take out here, then we have this structure. Yeah, so this is applied in creating such as piezoelectric or generator. Maybe we can use also this for creating the thermoheater, thermoheater or thermoelectric. So this is the result of the molding process. Some other lithography process can be found here. We have photolithography by using contact or proximity printing. E-beam lithography, this is the process that's commonly used in to create much smaller features. Yeah, down to 5 nanometer can be a pattern using e-beam lithography, and also focus ion beam lithography. Here we have also soft lithography, nano imprint lithography. This is also for NEMS devices, and depend lithography. Okay, that was about lithography. So now we come to the third section, material growth and deposition. This is common MEMS process techniques, basic technique in MEMS process. We can find this process include wet and dry thermal oxidation for sacrificial layer, for creating the passivation layer, coating layer, or to create the dielectric layer, or also to growth some oxide layer. So deposition also include spin coating process, such as spin coating of photoresist, oxide, mold material, composite polymer, silicon on SOG, yeah, silicon on glass, any other low viscosity material. Also include process of metal deposition, such as vacuum, thermal evaporator, sputtering, e-beam evaporator, etc. Also electroplating. So this process actually is non-CMOS IC compatible. Some other technique, namely deposition, creating of epitaxial layer using vapor phase, low pressure, or MBE, yeah, and also chemical vapor deposition using MOCVD, LPCVD, etc. This all process we call as a deposition process or material growth process. Okay, this is one type of deposition process, namely oxidation. So we can be divided into two process: wet thermal oxidation or dry thermal oxidation. This is the process which is available in our laboratory. The oxidation process is used to grow or to deposit oxide layer, such as dielectric, sacrificial, such as for mask, etc. Yeah, or for surface modification. So this is the schematic of the instrumentation of the equipment. Okay, the system consists of furnace made of quartz, a heater element to heat the chamber. We have here also gas system to deliver reaction gas into the chamber, consists of oxygen, nitrogen, or ammonia. And also here the sample holder also made of quartz. So here we put our sample, yeah. Then kita masuk ke dalam, let the gas in, yeah, heat the chamber. So the process can be start here. This is the photograph of our thermal oxidation. This is our quartz tube. Here inside we have heater element. So here we can see that the heater element is on, so the chamber is heated, yeah, here inside. For dry oxidation, use only gas, use only oxygen, yeah, flowing into the hot chamber, and finally react with our silicon. Then the result is a silicon oxide layer. Yeah. Wet oxidation, we use water vapor, flowing in, flow into our hot chamber, and reacts with silicon. It grow silicon oxide layer. Yeah. The chamber for this process use high temperature up to 1000 degree. Okay, dry oxidation has a lower growth rate than wet oxidation, although the oxide film quality is better than the wet oxide film. Therefore, thin oxides such as screen oxide, PET oxide, and especially gate oxide normally use the dry oxidation process. Yeah? The dry oxidation also result in a higher density oxide than that achieved by wet oxide. So it has a higher breakdown voltage, yeah, for diode application. In case of wet oxidation, the water vapor is used instead of oxygen. Yeah? The water molecule can dissociate at high temperature to form hydroxide that can diffuse into the silicon, yeah, faster than molecular oxygen. Therefore, the wet oxidation process has a significantly higher oxidation rate than the dry oxidation. So if you want to grow a thick oxide layer in a shorter time, so we can consider to use wet oxidation process. So this is also an example for oxide grow process use we call as for surface modification of silicon microchannel. Here we can see our initial structure has a threads having a trench width about 2 micron. So then we bring our sample silicon trench. This is silicon trench. Our sample into our oxidation chamber. Then we flow oxygen in a heat chamber, the result is the growth of silicon oxide layer. Yeah. Okay. Through this process, by this process, the silicon trench can be reduced. The weight of the silicon trench can be reduced. We can see here it reduced almost 80% from 2 micron down to only 1 micron. So this process also used to make the surface smooth, more smooth, yeah, smooth. So therefore, we call this process as surface modification. Okay, next deposition process we call as sputtering. Yeah. Sputtering process is another method to deposit metal and dielectric material. Yeah, the system consists of vacuum chamber, gas system. So we can let flow the nitrogen or argon as the reaction gas here. Argon is the reaction gas. Nitrogen is used as a purifier gas, to purify the chamber. Then we have the vacuum pump system, include the turbo pump and rotary pump. The power system, we have RF power and DC power, and the sample holder for anode. So we put our substrate here, and then for the target holder, we call as cathode here. The metal that have as the target material for deposition. A sputtering is a mechanism to release metal atom from its surface. Yeah. So when atoms are dislodged from the surface of a target material, resulting to collision with high energy gas particle coming from argon. So the high energy particle used in sputter deposition are generated by glow discharge inside the chamber, which is created by applying high electric field between anode and cathode. Yeah. This glow discharge creates free electron, within the discharge region. Yeah. So during the sputtering, the target is bombarded by the ion, argon ion, causing the release of target atoms from its surface and ejected surface atom are deposited. So the release atom will be deposited onto the substrate. So the final result is the new metallic layer on the substrate. This is the photograph of our sputtering system, which is available in clean room, in building engineering building, in MEMS clean room. RF power is used to deposit metal and also dielectric material, while DC power is used only to create the metal to deposit the metal layer. Another process to deposit the metal material is the thermal evaporation. This is a common and simple technique for deposition of thin metal, also commonly used in IC technology. The system consists of vacuum chamber, purifying gas, purifying gas, sample holder, and target holder, made of tungsten spiral, and powering system. The evaporation of metal take place when appropriate high current, in a high vacuum condition, hits the metal target, so it begins then to evaporate rapidly into a mono atomic state when the temperature has been raised, so, sufficiently for evaporation. So if we hit the tungsten, then the target metal will be evaporate and deposit on our substrate. This is the photograph of our equipment. Okay, that was the material deposition. So now we come to the material removal process. This is the schematic of the material removal process. So the left schematic is the material removal through etching. The right one is the material removal through lift off. So we can see here the difference of the process. For the material removal through etching, first we have here the metal layer that already deposited using either by using sputtering or vacuum evaporation, and then we coat our photoresist. We do the first photolithography. So we coat photoresist and then expose. So we have the photoresist pattern here. This pattern act as the mask to prevent this area during etching. Then we etch. So we have this structure. So we have this metal. The final process is remove the photoresist. Then we have the first metal layer. This is another technique also to create the structure. We call as lift off. So we create first the pattern. This is different contrary to this one. So we have first the metal. Here we have first the metal pattern, and then we deposit the metal. So we have the metal layer here, and then we remove the photoresist. We lift off the photoresist using acetone. So we call this process as lift off. So once the photoresist is removed, the metal over the photoresist will also remove. Will also be removed. So finally we have this structure, the metal like this. Okay. I mentioned about etching. So this is the process etching. The material removal can be done using several ways, such as etching, laser ablation, or lift off. So here we talk about etching process. This is the technique to remove the unwanted material. This process consists of wet etching and dry etching. For wet etching, we need liquid etchants such as acid or hydroxide. In dry etching, we use etching gases or plasma. For physical etching, normally the process is done through the impact of atom or ions, and also reactive chemical of ions. Another technique is using enhanced by RF energy instead of temperature. Most micromachining is presently done with silicon, and a large amount of that is etching with wet chemical. So our substrate is commonly made of silicon. Therefore, there are two types of process etching, namely isotropic etching and anisotropic etching. Because silicon is crystal, yeah, it has a certain crystal orientation. So this crystal orientation can be used to create certain structure inside the substrate. So isotropic etching mean that this solution attack uh, any direction inside the silicon substrate. So it give rounded profile. While an isotropic etching, it consider the crystal orientation of the silicon. Okay, this is the schematic of the isotropic and anisotropic wet etching. So we can see here, this is the effect of the non-orientation etching. It etch every orientation. Yeah? So it will create the round shape of the silicon strands. If we use some agitation, the strands will expand. Yeah, the depth of the strands will reduce. Okay, this is some application of isotropic etching process. We can create a microneedle. Yeah. So if you put here the same um, pattern in a low distance, so we can have here. So we can have a needle shape, yeah, with tip of the microneedle up to only 50 micron in diameter. This is the anisotropic wet etching. If we use surface silicon with 100 orientation, crystal orientation, then the wet etching will result V-shape, yeah, of silicon trench. You can see here. So this is another type of etching result if we use silicon having 110 crystal orientation. This structure can be done to create a hole, micro hole, small hole, for inkjet printer or for to create. We have here the V shape, and we have a small hole here down to 5 micron. Can we create? This can be used for inkjet printer opening, nozzle inkjet printer, etc. Okay, this is another type to remove unwanted material. We call as lift off. Lift off is a technique of patterning fine metal layers on a substrate such as a silicon, gallium arsenide, or indium phosphide. Yeah? So the process is so named because of the dissolution of lifting of the metal, yeah, metal covering photoresist. This is the metal covering the photoresist in photoresist sulfur solution. It is one method for removing unwanted metal after patterning the wafer. So I have explained before. Yeah. Okay, that's all the material remover. Now we come to the last section. I want to show you a case study for a process of MEMS device. This is the case study for the fabrication of electromagnetic actuator. This actuator can be used for many biomedical application, such as for as micro pump to deliver to drug delivery, to deliver insulin here, or for as micro pump for uh, wearable dialysis system, yeah, and also for use for hearing aid as micro speaker for hearing aid. This is schematic of our actuator. This system consists of a movable membrane, which is which can push and pull. Um, okay, consists flexible membrane, magnetic chamber, here magnetic chamber, and then coil, and then permanent magnet uh, attached to the membrane and located perpendicular to the coil structure. So if we put voltage here, so they will create a magnetic flux, yeah, then interact with magnet, and then generate power force, yeah, magnetic force that will be able to push and pull the membrane. This is the workflow, the whole workflow, but our section now is about this mask making, fabrication, testing, and characterization. Yeah, we have already discussed this in our previous section. So here's the simulation. So for this part simulation, we can yeah, um, yeah, we can create here the substrate, yeah, coil, and we have also permanent magnet, and this is the membrane, yeah, and we see the magnetic field profile generated by this coil, yeah, and we analyze the electromagnetic force, yeah, that generated by the coil, and then we can also simulate the membrane deformation by varying the type of the membrane, the circular one, square, or rectangular, and then we see the deformation capability of the membrane. We can also analyze the von Mises stress of the membrane. We can see also how high the membrane can be deflect, and also we can see also the material parameter, which one is the best one. So we this process called as the design, MEMS design, and then we bring our design to the clean room. So we fabricate. This is first one is fabrication of the coil. So we have here PCB coated with copper. Yeah. So here we we make first photolithography. We have the pattern, and then we etch the metal. So we have here the photomask. Yeah. This is the photoresist after uh, uh, expose. So we have the pattern, from this photomask. Then we etch using copper etching solution. We have this. Yeah, this is the common process in PCB technique. Yeah, so we have this structure, the copper structure on PCB. The process in creating this copper structure. Yeah, so here we can see here we have photoresist applied. So we applied photoresist here, and then we spin coat. We have a spin coating, and photoresist after spin coat, then soft baking, and then we etch. This is our mask aligner instrumentation, yeah, to create the pattern. While this one is the photomask. This is the result. So we have here the coil pattern. So you can see here the size is about 100 micron. The whole size is much smaller than 5 cent, our 5 cent money, shilling. Okay, here if we see under microscope or under SEM, so we have this the pattern, and this pattern look like here in our SEM. We can also observe how thick is our metal, this copper metal layer. This about 20 micron. We can observe also the size and the distance. Yeah, so we can analyze how high is the error. Yeah, or sometimes the metal trace will be smaller than our design. That was the planar coil fabrication. Then we have another process, namely to create the membrane. Here we have the silicon coated with silicon nitride, and then we create the pattern using photolithography process. Then we etch. Yeah, we etch the silicon until we got a certain thin layer. So we have here the a membrane. So this is the photograph, the process. We have this pattern, initial pattern, and then we etch using anisotropic etching. This process. This is the result. So we can see here some area damage. Yeah, are damaged. This white areas, namely no membrane anymore. Okay, this is the result of our etching. This is the SEM process. We can see the trends here and the layer as the membrane. For our actuator, we gum this magnet, attach magnet on the membrane. And then finally, we bond our planar coil with the prefabricated membrane. So we have here the membrane here of the silicon, having the thickness of about 2 micron, 2 to 10 micron. We can see here also the trends. So this material is attached onto the planar coil. So we gum. So we have an actuator system. So this is the membrane. Underneath the membrane is our electromagnetic coil. After finishing the fabrication, so we do the test, membrane deflection test. So we we put a power supply, we connect a power supply to the coil. Then if we on, so the magnet will generate force, yeah, to push and pull this membrane. So the height of the membrane deformation can be measured using our laser displacement meter. So we can also measure the height of the magnetic field. So this is the result. So we see some effect of the coil parameter, such as the number of winding and so on. Yeah? So there is effect of the coil parameter on the displacement of the membrane, and we also finally we can test the functionality of the device, namely by giving an input AC current, AC voltage, yeah, on, off, on, off, on, off. If we on the power supply, so the membrane deform up to 1.4 micron. If we off, it come to the initial download, displace down to 0.2. If we off, down, off, and down, on, off, on, off, on, off. Yeah. So this is the functionality test of the actuator. Okay, that's all my lecture today. If you want to know more about MEMS, so you can refer this book, Design, Manufacture, and Scale by Tai Ransu, or Fundamentals of Microfabrication for Mark Madu. Okay, thank you very much. Assalamualaikum. If you have any question, so please. Any question? Dr. Ronira masih ada? Okay. Okay. What minimum area we can pattern? Okay. If we use photo transparency, plastic transparency as the mass, we only can create the pattern up to 30 micron. If you order the mask on chrome material, so we order, normally we buy this mask from outside, from Singapore or Korea, we're able to create pattern up to 5 micron. Yeah. Yeah. Okay. Oke ya, itu saja ya. Okay, thank you very much. That's all my lecture today. We have assignment. Yeah. Yeah. Actually, this assignment. Okay. Yeah. Actually, this assignment have to be submitted until tomorrow ya, pukul 11 malam ya. You can submit, I think you can submit through this Microsoft Teams, and also please submit also to my email ya. Yang mana satu yang berjaya, itu sajalah ya. Kita try kedua-duanya. Ya, try kedua-duanya, hantar by Microsoft Teams, hantar juga by email ya. Hantar submit by tomorrow. Oke? Okay? Okay, that's all my lecture today. I think Dr. Onira can stop recording. Bila pelajar nak semak semula, if you want